We are live.
Diploma Studies, Park University. Hello. Hello. Am I
Yes,
audible?
Yes, madam, you are. Please begin.
Oh. Good afternoon, everyone. I'm Jyoti Napo, Assistant Professor, Chemical Engineering Department at Parul Institute of Technology, Diploma Studies, Parul University. So today we will discuss about heat transfer and its application in detail. And for that, we have an expert with us. I'd like to introduce our expert, Dr. Piyali Roy Chaudhary, PhD in Department of Rubber and Plastics Technology, Madras Institute of Technology, Anna University, Tamil Nadu. She has done for BTech Chemical Engineering from Haldia Institute of Technology, Haldia. Master of Chemical Engineering from Jadavpur University, Kolkata. She has done her PhD in Chemical Engineering from CSIR, Center Glass and Ceramic Research Institute, Jadavpur University. She has been titled Chartered Engineer by the Institution of Engineers India. Ma'am has published articles in Science International journals with high impact factor and presented papers in national and international conferences and workshops. Her research interests include membrane separate wastewater treatment, rubber filler reinforcement, and optimization techniques. Ma'am rich experience in process design and engineering of ultra and high pure water in pharma and food industry. Ma'am has developed ultra filtration ceramic membrane for critical applications. Moreover, Ma'am was awarded with CSIR SRF fellowship. Ma'am is having a very vast experience spanning over 12 years in industry research as well as teaching. So let us give a warm welcome to Dr. Piyali Roy Chaudhary. All over to you, ma'am.
Thank you, Jyoti. Thank you very much. You gave a nice introduction to me. And I also thank you for organizing this webinar. And I would also like to thank Parul University for giving me this opportunity. Be like a guest. Okay, so today my topic is heat transfer and its applications. Okay. So I am going to start. So I have arranged like this. First, we will discuss about some few basics of heat transfer. Okay, different modes of heat transfer we will learn, and then finally the applications of heat transfer. And the current research about heat transfer is going on, that I also discuss. Okay. So in introductions, what is heat transfer? Why we should learn and why we should study heat transfer? Okay, so we need to learn or we need to know or understand the heat transfer, basic principles and some rules, some correlations. Okay, and you know that heat transfer is we have a lot of examples in our day-to-day life for heat transfer and that is actually related with some basic principles and some correlations. That everything that is related to heat transfer we need to understand. Okay, and this then the point is heat transfer applications in different sector. Heat transfer is like that, it's related almost in every sector. If you go for any chemical industry or automobile industry or any other pharmaceutical industry, you can see that heat transfer different type correlations is there. Okay, and this heat transfer applications also involved in our day-to-day life. So one more important point is that heat transfer and thermodynamics looks like the same, but it's actually not. There is a differences between thermodynamics and heat transfer. So what is that differences? Heat transfer basically that is related to the temperature gradient. So what is the temperature gradient? That is the differences of temperature with some through length. Okay, and in thermodynamics it's related to some end point. Okay, so this basic differences in thermodynamics and but both heat transfer and thermodynamics both are related to temperature. So it seems like that both are same. So this very this differences is in between this heat transfer and thermodynamics lies. So it's heat transfer, again I'm repeating, heat transfer is due to that temperature gradient, and that thermodynamics that is related to some end state of process. Before going to heat transfer, first one thing we need to clear, that is heat. Then we have to come to transfer, heat transfer. So basically heat is like initially it is connected to the thermodynamics. So like we know that all matters that poses energy. Now this energy may be like potential energy, kinetic energy and internal energy. So when a body interacts with another body or its surroundings, so what will happen? That energy may undergo change, because every body that poses energy. Now this body is connected to another body, so that time some change will happen in energy. So that interactions of that body and with its surrounding, that can be classified as the like work interactions or like heat interaction. So this is the basic difference you need to understand. So heat is connected, and where work interactions is connected. So basically thermodynamics that deals with some study of like equilibrium, energy and transformations from one form to another form. Okay, so later we'll learn about in details heat transfer, different correlations. Okay, the next point is heat generations. Okay, heat generations, yes, this example we face our day-to-day life, like mobile or laptop. So after using mobile or laptop, what is happening? So it is getting like hot. So why hot? So like functions of like mobile and laptop, that is that functioning is related to heat transfer. So but here we need to control that heat transfer, otherwise that mobile or laptop will function not properly. Okay, so we learn how to control in that small devices. So again you have to learn, or again you have to study heat transfer to that accommodate that principles in this small device. So heat generation or heat build up into that devices and its control, for that you need to study heat transfer. Okay, so another point regarding this heat transfer, that is you can see in many chemical industries there is a lot of, there is a very big equipments or devices that produces a huge energy, but after generation some like some products, so some there will be some loss of energy, but we need to make like that we need to reuse of that energy, we need to minimize of that waste of heat energy, so that the plant will be more economic. So we have to design plant like that it is minimize that waste heat loss and reuse of that heat. Okay, so that we can make more economic plant design. Okay, so I'm going to the next slide. So objectives. What is the purpose of to study the heat transfer? What are the objectives of heat transfer? Okay, as I mentioned that we need to understand some basic heat transfer mechanisms. So everywhere you are going, you are handling some equipments that is related to heat transfer. For that, you need to understand that mechanisms. Okay, and also that objective is to study or is to learn or is to understand the modes of heat transfer. We know the basic three modes of heat transfer is there, like conduction, convections, and radiations. Okay, and the next is the materials, the different materials that are used for heat transfer process. That thing we need to also learn. And yes, that heat transfer equipments, their working mechanisms, then this also you can learn through this study of this subject. Okay, move on to the next slide. I think students are now maybe studying in heat transfer or already studied heat transfer, but still you need some clear about some basic concepts so that you'll do better in your exams or for further knowledge. Okay. So now, what is our aim? So aim is like how we minimize the waste or how we efficiently utilize heat transfer in a more economic way. Okay. So how we can do that? So to do this work efficiently, first thing we need to understand some heat transfer principles. Okay. So again, I think okay. So again, my slide is visible, Jyoti. Oh, okay, okay, okay. So thing is that before going to the next one, first we need to understand about heat transfer. So heat transfer is nothing but that energy in transit that is due to only temperature difference. It's like temperature difference is the cause, and what will be the effect? The transfer of energy, the form of heat. So temperature difference is like cause, and energy transit, that will be like, or rate of heat transfer, that will be that effect. Okay, so this process of heat transfer we can explain by only two terms. You see that heat and temperature. Okay, so heat actually flows from one point to another point. Suppose from one point at higher temperature to one point at lower temperature. But how? How heat is flowing from one point to another point? How heat is transferred from one point to another point? For that, we need to learn about modes of heat transfer. Then only we can able to answer this question, that how heat is transferred from one point to another point. Yes, the next slide, that is modes of heat transfer. Here you can see that we all know that three types of heat transfer mode is there. One is conduction, convection, and radiation. Okay, so see, I will discuss one by one. Okay, first I'll make some clear about basic principles. Then I'll go with some correlations of like conduction, convections, and radiations. Okay, first thing you can see in this picture. So some the water is some boiling. So many parts are involved. You can see metal part, I have mentioned that conductions, but I have mentioned convections in liquid part, and through coil part, that is radiations. Okay. Now, what is that conductions? For conduction, you need a like continuous medium. Okay. So temperature here, the temperature gradient exists in a continuous medium. Okay. So heat is conducted by the transfer of energy of motion. Okay. So molecules are there. Molecules are fixed. So how the temperature is transferred? So temperature is transferred through that energy of that motions of molecules to where? That between adjacent molecules. So one molecules and its adjacent molecules. Through that motions of energy, heat is transferred, though the molecules are not moving to anywhere. Okay. So molecules are static at their place. Okay. So that motion is internal. So how that energy transferred to that adjacent molecules, like vibrations, you can see that picture, vibrations, rotations and oscillations with that nearby molecules. Okay. So like if you touch any heated surface or any hot surface like table, so table and that molecules are not moving, still you can feel that temperature. So how that molecules do not moving, molecules only what is doing, that vibrating, rotations or oscillations, like that that internal energy is transferred to the next molecules. Okay. So that molecules what is happening, the collisions between molecules is happening. Okay. And that's how that collisions of molecules tends to equalize the thermal energy of the molecules. Okay. So we can conclude like that when molecules collide against one another without moving of fixed positions like solid, this mechanisms of transmitting energy is called that conduction. Okay. So you just remember one thing in conduction part, that molecules are not moving, they are fixed at their positions. So how they are that heat is transferred only by vibrations, rotations or oscillations. You just remember this only one part. Now coming to that convections. So convection, again, this is the that another modes of heat transfer. If the molecules is free to move, so here you can see that in conductions molecules are fixed, but here in convections molecules are moving. So some mixing is going on. Okay, so how that heat is transferred here, like you can see that, you can just refer that picture. What you are observing, like some water is there in kettle, and you are applying heat at the bottom surface. So what is happening, so you can see that here in convections motions of that body, that means the body itself carrying heat within this system, that molecules itself carrying heat. But in conductions molecules are not moving, here molecule itself moving and carrying heat. Okay. Now these conductions may occur in both liquid and gas. Okay. So you can see this picture. Now look at that bottom of this kettle. So it's a higher heat. This surface is getting higher heat. So what is happening? That water, that cold water, after getting heat, that density is decreasing. So what will happen as the density is decreasing? So as the density is decreasing of that part of water, so it will go up, it will go rise. Okay. So as it is going up, so there will be like one vacancy or vacuum. So what will happen? So to fill that vacuum, the nearby cold water will come and it will fill that part. So it's like a circular motions. You can see there is some circular motions. Like that, each and every molecules are moving. So each and every molecules are mixing, and that's how heat is transferred. Now in convections, you can see that two types convection is there. One is like forced convections, and another is natural convections. You can see this picture. Actually, many things are there in heat transfer. I have just incorporated few conceptual parts. Okay, so in forced convections, you can see that first you need to learn about natural convection. Then I will go for forced convection. So natural convection, what we know that convections is for fluid. It may be liquid or it may be gas. Okay. Now this is the red color. This is like some heated surface, and that surrounding air, that surrounding cold air, it is coming, and after contacting with that hot surface, it is taking heat, and then it is passing through. Okay, so natural convection is like only that due to the differences of density. So you can feel that there is some breeze, so the air is flowing, so due to that density differences. So cold air have higher density. After getting in contact with that heated surface, hot surface, it will go up. So it's the like motions of that part of that air. So there will be like breeze. So slowly it will get that heated surface will that it will get cooler, and the air, nearby air, will get heat. Okay, so this is like natural convection. So naturally it is the heated surface is cooling down and air is getting warmer. Okay, so when now look at this forced convections, what we observe, same thing is happening, but we are applying some external source. What is that source? That fan. You can add some external source like fan, pump. Okay, so forcefully we are helping, we are conducting to for convection, for conducting heat transfer. Okay, so forcefully we are doing, forcefully we are conducting like so that that heat transfer time will be less. Okay, so you can see that this fan is actually helping to fast passing through that air uh, to that nearby hot surface, so that quickly it will transfer heat nearby air and it is getting warmer, that air part. Okay, so this is like forced convection. Okay, so the next part is radiation. Okay, so this is the last modes of heat transfer. We already learned about conductions and convections. This is the another type of mode of heat transfer. Okay, so normally this radiation is like transfer of energy through space is happening only by electromagnetic waves. Okay, so through electromagnetic waves, radiation is occurring. Okay, you can see that that flow chart, like this electromagnetic waves emitted by a molecules because of internal motions. We are talking about that radiation is by electromagnetic waves. Now, where electromagnetic waves are emitted, how it's generated? It's generated by a molecules. Okay, when molecules of some when there is some internal motions. Okay, now this waves that is absorbed by a second molecule. Okay, so that internal motions, electromagnetic waves that is emitted by a molecules due to that internal motions, that energy is absorbed by a second molecules. Okay, and that's how it is converted to heat. Okay, now this internal energy of a substance is converted into radiant energy. Okay. So first remember, first that internal motions, and then internal motion is transferred to that nearby that second molecules, and that's how it is converted into some radiant energy. Now thermal radiations are only that you can termed as radiation that occurs without any medium. Okay, without an intervening any medium. So there is no requirement of medium to generate radiant energy. Now, again, I'm summing up that first thing, there is an internal motions, and that's how that electromagnetic wave is generating, and it is transferred to the next molecules, and finally they are converted into heat. Now you can term as this radiant energy. Okay. Now this radiant energy or thermal radiations is a small part of the total electromagnetic spectrum. So it's the only few parts. So thermal energy, now this thermal energy is getting converted into radiant energy. Okay. Now this radiant energy like partly absorbed, some part will reflect and some part will transmitted. Okay. So what we know, this formula you can refer, alpha plus nu plus tau equal to 1. So if you sum of this total absorbed and reflected and transmitted amount, we are getting some unit value. Okay. Now here this alpha, what is denoting by alpha? That is total energy that absorbed. Okay, which is characterized by the absorptivity of the body. So what is meaning by nu? Nu is like energy reflected. So sorry, it's getting. Yes, some voice problem. Okay, so you can see that some tau. So you can tau is like some part that is transmitted. So you can term as a transmittivity of the body. So later on we'll learn when we are getting that fully that if alpha equal to 1 and the others are 0, what is calling it? The next slide in radiation part we'll learn about that. Okay, so as I mentioned, after some basics, I will do some correlations. You can see that conductions.
Actually, slide is not visible. We connected that.
Hello, ma'am. Hello, ma'am. Any problem? Hello. Hello, ma'am. Am I audible? Priyali, ma'am.
Hello. My voice is audible,
Yes, ma'am. It's audible.
and you can see my PPT.
Yes, ma'am. It's visible.
Okay, thank you. Sorry for some network issues here. So I'm talking about induction. Sorry, I'm talking about some conduction. So in conductions, we have the Fourier's law, and now we can see that how that heat transfer is related to the temperature gradient. Okay, so you can see this correlations that dq by dA equal to minus k the dt by dx. Okay, so that right part, this is temperature gradient and this is flux. So while you are remembering that Fourier's law, you just remember two things that is related only the flux and temperature gradient. Okay, so here that the dq is the rate of heat flow. Now, what is that K? K is called this is the proportionality constant, and it is called the thermal conductivity, and its unit is like in SI watt per meter Kelvin. Okay, so and you can see also some area is also involved, and T for temperature and X. This is the length of conduction path. Now look at this right side image. This is like one bar or box. Okay, so one side had the higher temperature like T1, the other side T2. So T1 have the higher temperature than T2. Okay, so this we need to difference in this part, delta part. So it will be like T1 minus T2. So higher temperature minus lower temperature. Okay, so you remember this part. So temperature gradient is not only del T or temperature difference. This whole part is temperature gradient. dt by dx is temperature gradient. So you can see that it's like the rate of heat flow is like a linear relationship with the temperature or differences. Okay. So now I'm talking about this proportionality constant, that is thermal conductivity. So here, thermal conductivity you need to learn, because this thermal conductivity actually means characterize some materials. Okay, here you can observe that you can see through this K, we can so K is like how easy heat is transferred from one point to another point. Okay, so material can be like characterized by K. Now some material have the higher K, some material have the lower K. Now look at this correlations. If K is higher, so what will happen? It's a linear relationship. So if K is higher, the rate of heat flow will be higher. Those materials have the higher K, then what will happen? The rate of heat flow will be higher. Okay, so material may have higher K and that poor K value. Okay, the material having that higher K, that will be very, like their heat transfer will be very fast. Okay, like wood, if you can see here some wood block and copper block. I have mentioned wood block and copper block. So copper block having the higher K. So what will happen? If these have the higher value, what will happen? The rate of heat flow will be high. So here the copper block, the rate of heat flow will be high rather than wooden block. Okay, because here the K value is very less. And this negative sign is nothing but that if your increase that this length X, if this X is increasing, then your temperature will also decrease. This is the meaning of that negative sign. Okay, so you just make I'm talking about this copper and wooden block, like silver. So metal, silver, copper, that have very high K value. So that means high K value, that means the higher rate of heat flow. But at the same time, the gas, okay, the gas is normally that K value varies 0.006 to zero point 0.6 watt per meter Kelvin. So you can see that for gas, I'm mentioning that very less K value. So what will happen for gas? Then rate of heat transfer will be very less. Okay. So, and then one thing that solids part, solid having very low K value, that you can use as a insulator. Okay, so K value, that means very less K value, that means very less heat transfer. So those material having very less K value, that can be used as a insulator. Okay, like fiberglass, polymer foams, that are normally used like a insulator. Okay, so that polymer forms is like entrapped air. So that's how their K value is decreasing. So that's how it's maintained its the temperature. Okay. So moving to that next slide. Okay. So here again, you can see that some basic correlation, some conditions is there. One is like for a steady state conditions, for a simple only from wall, how heat is transferred. Okay, so here for a plain wall, you can see that that del T by R. So R is nothing but the thermal resistance. So what is that? That X by Ka. So you can go back to that earlier slide. You can see that Ka del T by X. So here, that's the opposite, X by Ka. Okay, so del T by R. R is thermal resistance. Very simple formula for only plain wall. Now, so here the bottom you can see heat flow through composite wall. That means some few walls that are combined. So how then heat will transfer? We learned about for single wall. So now when there was many layers, so how heat will transfer? You can see that you have to individually calculate that resistance, thermal resistance. Okay, then you have to add all that resistance, and you know that del T by del R, that is the rate of heat flow. So for entire series like layer 1, layer 2, layer 3, you need to add that resistance 1, resistance 2, resistance 3. The finally you are getting sum of all these 3 layer resistance. Just divide with the temperature differences with that summations of resistance, we will get the rate of heat flow. Okay. So here now that you can see that temperature differences. So from del T1, del 2, this if this is a higher temperature, so here will be maybe some higher temperature, here less, like that, heat is maintained. So that if we stand here, we are not feeling too heat and that the lost surface. Okay, so like this is very easy. Okay, so you need to just add a sum of all the resistance, and then you need to divide the temperature differences and then resistance. Okay, now these two for plain wall. So what will happen for cylindrical wall? Okay, so shapes are changing. You can see that here the condition is same like steady state, and this is valid. That Fourier's law, that is valid for steady one-dimensional flow. Okay, now for cylindrical wall, you can see like it's a that radius, inner radius and outer radius. Okay, so you'll have some inner radius and outer radius. So inside one temperature will be there. If the liquid is flowing, that hot fluid is flowing inside, obviously the temperature will be higher at inside. Okay, and TO will be that outside temperature. So Ti will be always greater than TO because hot fluid is flowing inside of that tube. Okay. So finally, and this area, you know, that cylindrical wall area will be 2 pi L. So put that area value. So you will get Q value. Okay. Now here, one thing very important, when this wall, okay, that tube wall is very thin, you can do that arithmetic mean of that radius. But if the layer is very thick wall cylinder, that means you want to control temperature by adding insulator, one layer insulation, second layer insulation, third layer insulations. Then how heat will flow through this insulations, layer 1, layer 2, layer 3. For that, your layer will be very thick. That time you need to calculate that log mean area and log mean radius. Okay. So yes, I'm going to that next slide. You can see here, if you have time, say I will discuss this thing. Okay. First, we need to complete the PPT. Okay. This is nothing but I just mentioned 2 problems. So how you can solve this for like one like a flat surface and for one cylindrical surface. Okay. This thing I took from Mackay-Smith book. Okay. I'll discuss it later. Okay. So I'm going to the convection part. Okay. So convections, that basic concept already cleared in previous slide. So what we know that convections, that molecules are mixing. So molecules are moving from one point to another points, and there is a making of like cycles of that molecules cyclic way due to that density differences is moving. Okay. Now, what is that correlations in that convections? So the basic equation for heat transfer, rate of heat transfer by convections, and obviously that condition is that steady state, that is Q equal to HA del T. Okay, so here this term, that is heat transfer coefficient. Now this heat transfer coefficient actually depends on some agitations and nature of the fluid. Okay, so this heat transfer coefficient is nothing but like measurement of some intensity of heat transfer, okay, between that surface of that body and its surroundings. Okay, so it's like some measurement of intensity, this H. Okay, now maybe 2 types, like individual heat transfer is there and overall heat transfer there. In convection, many things are involved, like phase change heat transfer, in phase change heat transfer without phase change. Okay, then boiling. So I'm not going to mention everything because time is very limited. So you can see that individual heat transfer coefficient. Here everything is same, only that you can see that temperature part, TW minus T average. Okay, TW means that surface temperature at the surface of the wall. Okay, this part is like fixed. Okay, now this is T average. Now T average, it's like depends on the flow. If the flow is laminar flow, the turbulent flow, this thing will change here in this part. Okay. Now for overall heat transfer coefficient, in overall heat transfer coefficient, what actually happens? When like some liquid is flowing or some fluid is flowing inside that tube, many things are happen. Like it is face some several resistance in series, like hot fluid film resistance, solid wall resistance, then cold fluid film resistance, then dirt or that fouling resistance. So many types of resistance are there. So you need to do some overall concept. You need to incorporate some overall concept. And here the T is like overall average temperature difference. Normally what you use the temperature difference, but here overall average temperature difference. Okay. This thing you can, this overall heat transfer coefficient you can use when some insulations layer is there. Then you know only that inside tube temperature and outside tube temperature. So that time you can use this to calculate that in between temperature and heat flow. You can use these equations. Okay, as I mentioned that many things are involved in condensation process, the convection process. I'm just mentioning only that condensation. Okay. Normally, two mechanisms are there for condensation. One is like drop-wise condensation, and the next is film-wise condensation. Okay. So what is happening in drop-wise condensation? Suppose some condensable vapor is exposed to a solid surface like this. This is like solid surface, and some condensable vapor is exposing this solid surface. When in that solid surface there is some formations of some droplets, and normally in this dropwise condensations, what is happening? It's not readily wet that surface. Okay, but in case of film-wise condensations, so there will be a light layer. Okay, so suppose outside this condensable vapor is there, it is in contact with this solid surface. After contacting this solid surface, it will make like a solid film, like a film. So in this type, normally what is happening? It's wet that surface. Tendency is to wet that solid surface, but here at dropwise condensation, that surface is not wetted by the drops or liquid droplets. Okay. Now here some phase is changing from vapor phase to like liquid phase. So the condition is the water vapor is cooled below its equilibrium saturation temperature, okay, at some specified pressure. Okay, so this is the only one conditions to formations of this dropwise and film-wise condensation. Now you can see here this picture. This is some time-lapse image of condensations. You can see how that droplets is formed, and after that you can see it's growing bigger, and it's now detaching from that surface. Okay, so after growing that droplets it's growing in bigger size. So what will happen? It will detach from that surface. But what will happen in film-wise condensations? It will make a film. After that, due to gravity, it will go down. Okay. So while it will go down, it will wet that whole surface. Okay. So normally the dropwise condensation has the higher value than film type condensations. Okay. And now when dropwise condensation is happening, It is normally occurs when this solid wall have any dirt is there, okay, or impurities are present, okay, and surface is contaminated, then drop is happen, okay. And normally that heat transfer coefficient for dropwise condensation is higher than the film type, that film wise condensation. It's like 5 to 10 times larger. Right. So I'm going to that next slide. That is radiations. So we already know that if we sum up this total like absorptivity, reflectivity, and transmittivity, it is getting one unity. So now this alpha is characterized absorptivity, this nu is reflectivity, and this the tau is for transmittivity. Okay. So now what will happen when alpha value is 1? That means absorptivity value is unit 1. The other thing, there is no reflection, no transmittivity. So the total radiations, that energy totally absorbed. So that time we can call that body is black body. Okay. Now when that absorptivity is 0, but reflective total, what is that incident is coming, that is totally reflecting. That time specular body we can talk. Okay. And the another condition is like absorptivity and reflectivity when 0. So the total that incident is coming, radiant energy coming, it's totally transmitting. Okay. So whatever is coming, transmitting, okay, or passing through. That time we can term that body transparent body. Okay. So through this radiation mode, we earlier I mentioned that the energy or the sunlight is coming to our earth through this radiation mode only. Now how that sunlight is coming by this radiation process, modes of heat transfer. Whatever is coming, that energy or thermal energy, that only 20 to 40% energy is absorbed by the Earth's atmosphere. So few parts will be lost due to some scattering by dust particle or some air molecules. Okay, and few parts will be like some reflecting, scattering and reflecting. So reflections like we lost some reflection like some through water, snow, and clouds. Okay, so we'll get that Earth atmosphere will get only 20 to 40% that radiant energy. Okay. So now this radiant energy fall at a constant quantity. That quantity, that amount of radiant energy is called that solar constant. Solar constant is like amount of radiation that is fall in like 1 minute on a black surface of 1 square meter that is placed at right angles to the sun's ray, the direction. Okay, right angle to the sun's ray. Okay. And obviously there will be no like atmosphere where present. That time you can term as a solar constant. Okay, so now we already learned about 3 basic type modes of heat transfer: conduction, convections, and radiations. Now we'll have some applications. Okay, so in applications, as I mentioned earlier, that almost all industries have some heat transfer equipment. You can see that in automobile, industry, you can see that in car, that cooling, that oil cooler is present. Again, you need to apply your heat transfer knowledge here. So here, that hot oil is getting cooled by water. Okay, so heat is transferred. That hot oil giving heat to that cold water, and cold water is getting hot. So here this oil is getting cooled by this cold water. Okay. Now again the next application is like chiller or evaporator. Okay. Again here you need to understand that heat transfer. This you can see different types of chiller or evaporator is there. Here what is happening actually, cold refrigerant passes through that this tube. Okay, and there is over this tube it is getting cooled, and it is also used for air conditioning purpose. The next slide you can see that applications of heat exchanger. So you can see that a lot of areas are there. You can use heat exchanger. So heat exchanger is how important for all this sector: pharmaceutical sector, chemical industry, paper and pulp industry, oil sector, refineries, AC ventilation system. So everywhere heat exchanger are used. So heat exchanger is nothing but a device which helps to exchange that temperature. Okay. Now again, if we go for condenser, what is happening? This is like cell and tube concept. So large number of tubes that are formed like a bundle. So this tube bundle is like mounted with inside like a cell, steel cell. Okay, and normally both ends are fitted, closed, or end cap is there. Okay. So again, another application like in thermal power plant. So in thermal power, this is the picture of thermal plant. This is a huge big part. This is the like cooling tower. Okay. So what is happening in thermal power plant? Thermal power plant, you can see that heat, that water is going to that boiler. After that, it's steam is generations, and steam is generating, and it will go to that steam turbine, and it is providing some electric generator. It is going to that electric generator. So the other part, it is coming down to that condenser. Okay. So from this condenser to exchange its heats, it's going to cooling tower. So that's how it's like a closed or circular way water is moving. So anywhere you can see that the heat is exchanging. So this is the solar water heater. Again, heat exchange knowledge is required here. So in solar water here, so what is happening? Like cold water is passing through that some collector panel. Okay, so this collector panel is placed into that sun. After that, it is absorbing heat. Cold water is getting that absorbed heat, and it is becoming hotter, and it will passing through this tank. Okay, that's how it is collected. So everywhere you can see some heat, some knowledge of heat. Okay, or heat transfer. Okay, coming to that last two slide. Our time is very limited. I think it's okay. I'll take only 1 minute. So what is going on? Some current research about heat transfer. You can refer through some current journals. You can refer some papers or articles. So you can see that there are a lot of research is going on considering this heat transfer. Just go through that slide. I'm not discussing in details. Some heat conductions. They are doing some researcher is doing some research on heat conduction for droplet dynamics. Yes. So where you can find that current journal or paper for heat transfer. Okay, you can refer that International Journal of Heat and Mass Transfer, that is for science student. You can also refer some other journal also, ACS and Springer or Nature. Okay, you just go and search what is going on, what topics are currently doing for heat transfer. Then only you can update yourself, and you can refer more recent topics. Okay, I'm just ending up my presentation. So if you have any queries, you can ask me.
Hello, ma'am.
Yes, yes, Joe.
Thank you so much. That was very such a nice presentation, and it was very informative. And hope it has helped our students to understand the heat transfer and its applications. Thank you so much, ma'am, for giving us your valuable time. And I also thank the Parul University and PU webinar team for providing the platform. Thank you so much, ma'am, for giving us your time.
Thank you, Jyoti, once again. And I also would like to thank Parul University and students. If you have any questions, you can convey to Jyoti ma'am, and she will convey me. Okay, so thank you very much for giving me this opportunity.
Okay, ma'am. Thank you. Thank you so much. We are signing off.
Okay, okay. So can I you please convey if someone have any questions? Okay.
Yes, sure, ma'am. I will message you.
Okay, okay. Thank you. So can I end up?
Yes, yes.
Okay.